Hello everyone, greetings from Team ELECTROSAL. Today we are going to present you project model number 708 titled Automatic Power Factor Correction with Measurement of Real Power, Reactive Power and Apparent Power with IoT monitoring. Now let us look at the hardware and then the working. Here you can see our automatic power factor correction system. In this project we are using an Arduino microcontroller which acts as the brain of the system. To detect voltage and current zero crossing, we have used two zero crossing detector circuits. These are built using operational amplifiers in comparator mode. One zero crossing detector is connected to the voltage signal and the other is connected to the current signal. The outputs of these circuits are fed to the interrupt pins of the Arduino. We have also used a relay driver IC to safely interface the Arduino with the relay module. The relay controls a shunt capacitor bank which is used for automatic power factor correction. An LCD display is provided to show the time lag between voltage and current along with power related parameters. Other supporting components include transformers, resistors, diodes, switches and the load lamp with the ESP8266 Wi-Fi module to interface with IoT platforms such as ThinkSpeak. Now let us look at the working part of this project. Now at this stage I am applying supply to this circuit. After applying to the circuit, the message to the LCD come as welcome. Then we will wait for some duration to connect it to the Wi-Fi. After connecting to the Wi-Fi, the readings will be shown. Now at this stage, no inductive load is present. Because of this, the current lag is 0. As a result, the reactive power is very low and the real power and apparent power are almost equal. This condition occurs because no inductive load is connected and therefore no capacitors are switched on. Now I will switch on the inductive load. In the next cycle, the system senses the change and we can clearly observe current lag into the LCD screen like this. Due to this, I lag, the reactive power increases and apparent power increases and the real power decreases compared to the apparent power. This relationship can be clearly explained using the power triangle where real power, reactive power and apparent power are related. The same effect can be observed here in our system. Since the current lag is higher, the controller automatically switches on two capacitors for the two capacitor. It will start the two capacitor for compensation. When the system enters the compensating mode, it tries to correct the power factor. However, due to continuous variation in power factor, the capacitor may switch on and off repeatedly. To avoid this fluctuation, we keep the system in lagging mode. Now as you can see, the system is in lagging mode, the capacitor fluctuation is eliminated. Even though the Arduino process only the inductive load waveform, the power factor is improved at the back end and we can clearly observe real power, reactive power and apparent power values. Additionally, the system also supports manual mode. Using the switches, we can manually add or remove capacitors and observe how power values change in real time. This demonstrates both automatic and manual power factor correction in our project. Data will be read by the Arduino that will be transmitted to ESP8266 Wi-Fi module and that data will be calibrated on the ThinkSpeak for the remote sensing purposes. You can see the different readings such as power factor, current, real power, reactive power and apparent power readings into the screen like this.